Hello and welcome to our STEAM project number 17, featuring the Raspberry Pi Pico and MicroPython. This lesson is part of our Sherpa level series, designed for the somewhat experienced STEAM teacher. Today's project is going to check the water quality in support of the Sustainable Development Goal 6, Clean Water and Sanitation. We will program a turbidity sensor to measure the murkiness of water and control a valve depending on the readings of that sensor. My name is Peter. I am the founder of Educomondo and a certified STEM instructor and course designer. The goal of today is to use a turbidity sensor to measure the murkiness of water. Water that contains too many polluting particles is unfit for consumption or use in a household. So we will understand the working of a turbidity sensor. We will link the readings or the output from the turbidity sensor to a servo motor that will act like a controlling valve. But most importantly, we make sure that you and your class work together as a team to find solutions, help each other, and present the project in a clear way. A turbidity sensor is one of the most common parts of a water purification plant. It makes use of a light source that is then captured on an LDR, which stands for a light-dependent resistor. Obviously, the darker the water, the less light will reach the LDR. The cleaner the water, the more light will reach the LDR. We can set thresholds to define what should be the minimum or maximum reading to either allow the water to pass through the pipes or to close a valve to prevent that dirty water gets into the water supply of people. The sensor comes with a controller board. On that board there is a small switch to change from analog to digital output. For our project, we will use the analog setting. As you can see, there are clips on the side of the sensor to mount over the edge of a glass. Only the part where the light source and receiver is should be submerged. Do not submerge the whole sensor, as that will create a short and it will destroy your sensor. For this project, we will need, first of all, the breadboard with the Raspberry Pi Pico, and don't forget the pinout card, the turbidity sensor with the control board, a servo motor, a bunch of jumper wires, 3 glasses of water, 1 filled with clean water, 1 slightly dirty, and 1 very dirty. Alternatively, you can also use some plastic filters in case you don't want to use water in your class or laboratory. And here you can see the finished product. The fritzing drawing shows the connection, so leave this open on your computer or project it on a screen so that you and your students can build the project accordingly. Now, before we dive into the program, let's revisit how to control a servo motor. And it's all about pulse width modulation, PWM. This generates a signal with varying pulse widths. And the servo position, so between 0 and 180 degrees, is determined by the pulse width of the signal. The duty cycle in PWM is the percentage of time that the signal is high or on within one period. And we use the module and classes machine and PWM to generate PWM signals with specific pulse widths, allowing precise control over the servo positions. So let's take a closer look at the calculations that we will need. The servo motor receives a pulse width modulation signal as an input, where the duration of the high state, so the on time or the duty cycle, within each PWM period determines the desired position. Typically, the pulse width modulation signal is set at a frequency of 50 Hz, typically for the type of servos that we are using in our projects. Now, as we know, 50 Hz equals to a period of 20 milliseconds, because it's 1 second divided by 50. Or, in microseconds, that is 20,000 microseconds. Now, the duty cycle will determine the angle of the servo motor. Typically, a duty cycle ranging between 2% to 10% represents the minimum angle, and between 10 and 20% it represents the maximum angle of the servo motor. In my case, or with the servo that I have been using, the duty cycle during a period of 550 microseconds, which equals to a duty cycle of 2.75%, gives the minimum angle position of 0 degrees. So why 2.75%? Where does it come from? Well, that is 550 multiplied by 100 and divided by 20,000. A duty cycle of 2,400 microseconds, or 12%, which is 20,000 multiplied by 12% is 2,400, gives the maximum angle of 180 degrees. So, for our program, you need to remember the percentages 2.75 and 12, because we will need these to calculate the input related to the pin range reading between 0 and 65,535 on the Pico. Let's now go to our Thonny environment for some live coding. Welcome to our live session, and as you can see, I have already prepared the program because it's a pretty short program, so probably easier to just follow along on the couple of lines. I've started with some comments, and specifically the last one may be a good tip. If you experience some weird readings from a sensor, it might be that you have to change the voltage, is that you have to use either a 5-volt pin or the 3.3 volt pin, because we have a mixed environment of 3.3 and 5-volt microcontrollers, but the sensors are sometimes calibrated towards 3.3 volt or sometimes to 5 volts. So that's a little bit of an experiment that you need to do. Of course, we are going to import our classes and our modules. We have just 2 pins that we need to define. We have a sensor pin and we have a servo pin. The sensor pin, because we have selected analog reading, we will use the analog to digital conversion on pin number 26, and we have connected our servo pin to our pin 16. That pin is going to use pulse width modulation, and as we have seen just a minute ago, with this type of servo, the frequency is most of the time set at 50, so 1/50th of a second. We are going to define a maximum and a minimum duty because we want to have either the valve which is controlled through the sensor, not through the sensor, but through the servo motor, is going to be either open or closed, depending whether we are going to send the maximum duty or the minimum duty cycle for the controlling of the servo motor. So this is just a quick rehearsal of what we have seen just a minute ago about the 12%. And in this line, we are going to extrapolate the 12% towards a number that will be read through the MicroPython, through the microcontroller, which is the maximum reading of 65,535. 12% of that is 7,864, so that's the maximum, and then the 2.75%, which is the 550 microseconds, that will drive the minimum duty. That 2.75% of 65,535 is 1,208. So those are the two numbers that will actually drive either a 0 degree or the 180 degrees. We will also have a conversion factor, 3.3 volt divided by the maximum of 65,535, or 2 to the 16th power. We will also have a low and a high reading. Now that low and high reading is definitely something to experiment with. In the best of all worlds, this should be 0 and 65,535. Unfortunately, I have found out that the low reading never reaches 0. So in my case, it always got stuck around 500. In your case, it might be higher, it might be a little bit lower. That is part of the calibration that needs to be done while you are running the project. That's all we need to do in terms of predefining our environment. So we can get into our while true loop. And what we will do is, of course, read the data of our sensor pin. We are going to translate that into volt via the data conversion factor of 3.3 divided by 65,535. We also want to display later on a percentage, and the percentage formula is that we want to have it here reflected as an integer, and we will have the reading from the sensor, so data, you deduct the low, so the 500, multiply this by 100 and divide it by the difference between high and low. The next couple of lines are 3 times a print statement. I've just given those 3 different ways of running a print command, so you can have a look at it. All of them will work and all of them will be more or less the same result. So the one that is the last one, so print and then our f function, the raw data in voltage, the percentage we will have, and so those 3 different parameters we will print in our REPL. And then we just have a sleep and delay of 2 seconds, just to make sure that things are not going too fast. That's for the reading of the sensor. Now we are going to use those readings and we will use those to control the servo with a very simple if and else statement. So the servo.duty U16, the duty min and the duty max is going to be else. So the duty minimum, if that is going to be below 95%, and I have used 95% because that was the percentage that I came up with while I was calibrating this project. For you, it might be slightly different. So if it is smaller than 95%, then we say we will close the valve. If it is larger than 95%, it will open the valve and the water can freely flow throughout the pipes of the people. And that's basically it. So it's a pretty simple program in order to drive and control a servo through the readings of a turbidity sensor. So I hope that it works for you too. Let us have a look at how it will react with our project and see how we are doing. So let's move to the next scene. The first glass is filled with clean water, and the servo should remain as it is in position 0 or as a closed valve. The next glass is filled with darker water, but still somewhat transparent. And the last glass is filled with very murky water, and obviously that is not acceptable. So let's start the program and dip the sensor in the first glass. You can see that the readings are in the high 90s, and nothing happens with the servo. We go to the next glass, and you can see that the sensor continues to read values in the mid 90%. But finally, we dip the sensor in the last glass and the percentage drops below the 95% threshold, and it activates the sensor motor to close the valve. If you are not very keen on using water in your class because it can become a little bit messy, you can also use opaque plastic filters to simulate the contamination. Here I am using some plastic brown filters, and you can see the percentage going down as I am putting one and then a second filter between the sensor. I hope this also works for you. If not, well, you know it and your fellow students know it too. This is no time to panic, but to conduct some critical review of the code and to check both error messages and the physical project. This project is a great starting point to talk about recycling water. Let your students do research on SDG 6 and what it really means. You can combine this project with the previous project and, for instance, build a recycling loop to capture the excess water from the plants and measure the turbidity after it has gone through some simple filtering. Turbidity is of course not the only measurement that water purification plants apply before releasing potable, safe water. So think about what other measures they could be using, and are there any sensors available to include in a more advanced project? And that's it for lesson 17. I'm confident that you and your class found it quite inspiring. In our next project, Project 18, we will create solutions for SDG 7, clean and affordable energy, programming a smart solar panel. I look forward to seeing you again. Bye-bye for now.